This is section 8.4, and we're going to work with De Moivre's theorem and then the roots of complex numbers. A complex number, remember, can be written in the form a plus bi if it's in standard form. And let's look at example 1 for a minute. Do you see how we have 1 plus I root 3? So that's a complex number, and then it's to the power 8. Now if we tried to multiply this out, it would take a while to write out the factors and then multiply them each together. And you'd probably find some patterns because I2 powers have patterns in them and eventually get to the answer. But I'm going to show you another way to do this using De Moivre's theorem, which is a little bit faster, I think, especially when the power is so high. De Moivre's theorem, if r times cosine of theta plus I sine of theta is a complex number, do you see how it's a complex number written in trig form or polar form? If n is any real number, then the following holds. So you're taking a complex number to a power. Do you see how you're taking the modulus to the power, and then you're multiplying the arguments by that same number? In the compact form, this is written r to the n, and then cis of n theta. So you'll be able to go through example 1, and then let's go on to page 815. Roots of complex numbers. Let's first look at what we have learned so far in algebra. You know that the square roots of 9 are 3 and -3, because 3 squared is 9 and -3 squared is 9. The square roots of -1 are I and -I. And the reason why is because you could take x squared is equal to -1, and then if we use the square root property, x is equal to plus or minus the square root of -1, which is equal to plus or minus I. Now the cube roots of 8, we know that 2 is a cube root of 8, but there are also 2 other roots, cube roots of 8. So it's 2, and the other 2 are imaginary roots. When we're finding nth roots, we're going to find out that there are nth roots of any complex number. The nth root for a positive integer n, the complex number a plus bi, is the nth root of a complex number if the following holds. You take some number to the nth power and you get another complex number. If we take 2 and cube that, we get 2 cubed. But there are 2 other imaginary roots that when you take them to the third power will also give you 8. The nth root theorem says that if n is any positive integer, r is a positive real number, and theta is in degrees, then the non-zero complex number has exactly n distinct nth roots. And what it would look like, each of the roots would look something like this, where alpha, see that's the new angle, is either equal to this or this. You can write it either as 1 fraction or 2 fractions, or if theta is in radians, you can write alpha as 1 fraction or 2 fractions. And to find each of the roots, you're going to take k equal to 0, and then 1, and then up to n minus 1. And you see that there will be a total of n roots for each of these. This looks a little bit messy when you first try to find the roots, but if you can find patterns, it's so much easier. After you try to follow the first example, see if you can see some patterns, and that will make it easier for you to find the roots.